Welcome to the photoelectric effect, part 4. In this video, we talk about the explanation by Einstein for the photoelectric effect. This theory by Einstein is what won him the Nobel Prize in Physics. A lot of people would guess that Einstein won the Nobel Prize in Physics for his theory of relativity or for E equals mc squared, but he actually won the Nobel Prize in Physics for his theory to explain the photoelectric effect, which became known as quantum theory. Or in other words, the photon theory. If we take a look at this diagram, is really helpful to understand what's going on here and make a connection between all the variables that go into the photoelectric effect. We start off with an incident photon, which is incident light. And we'll get to this more in a bit, but Einstein came up with the theory that in addition to light having a wave-like nature, which we studied earlier this year, it also has a particle-like nature. And those particles of energy he called quanta, or photons. So we have incident light, so incident photons coming down and hitting the metal surface. What is clear by the previous work before Einstein is that the energy of this light is equal to h times f. And several proved that before him. This is not something that new that he came up with. For example, Max Planck, we just take a look at all his work. He's the one that really developed a lot of this information. So Einstein's kind of riding on the coattails of a lot of work of a lot of other scientists here. What's important to understand in this diagram is that the frequency of light that's hitting the metal plate is greater than the threshold frequency. Remember in the last video we talked about the minimum frequency with which electrons were just ejected or just removed from the metal. This frequency that's hitting this metal is greater than that frequency. Okay? Alright, so now we go down here at the bottom and you can see this electron right here is just being moved to the surface of the metal. That would require energy. So it's going to use up some of the incident energy to do this. How do we calculate the energy? Well, any kind of energy in the photoelectric effect is calculated by h times f. But this is the special kind of energy that requires the minimum frequency to which the electron is just ejected. So this amount of energy required to just remove the electron to the surface of the metal is called the work function. And the symbol for that is a lowercase Greek letter phi, which would be spelled P-H-I, and it's the symbol for work function. I would encourage you to add that equation to your reference table. Phi equals HFO. All right? So now imagine this. The frequency of the incident light is greater than this frequency required to just remove the electron. What does that mean? That means the amount of energy hitting the plate, hitting the metal, is greater than the amount of energy to just remove the electron. So where does the leftover amount go? The leftover amount gets imparted to the electron in the form of kinetic energy. And it's that max kinetic energy that was being measured in Planck's experiments by adjusting the stopping potential, etc. Remember, the kinetic energy we can measure, calculate by 1/2 mv squared. And sometimes you are asked to do that. Okay? Now what's really important here is to put it all together. So, how does the energy hitting the plate, the energy required to just remove the electron, and the kinetic energy the ejected electron has after it leaves the metal all relate? Well, clearly we can make this connection. E represents the total amount of energy available. It's the total amount of energy hitting the metal. Phi is the amount of that energy used to just remove the electron. Then the leftover amount gets imparted to the electron in the form of kinetic energy. So E, the total, we call phi, the amount used up to remove the electron, plus the leftover amount imparted to the electron in the form of kinetic energy. E equals phi plus Ke max. Now what we're going to do is show some other derivations here. How do we calculate E? Well, that would be HF. Phi is HFO plus Ke max. If we take and subtract HFO from both sides, that would give us HF minus HFO equals Ke max. And then if we distribute out the H, Planck's constant, that would be H times the quantity, F minus FO equals Ke max. This is what is called, and often used for the expression, for what is called the photoelectric equation. I would encourage you to add this equation to your reference table. Okay? Now, this puts all the pieces together as far as what is going on during the photoelectric effect. And to this point, all of this information was already available. So they knew the photoelectric effect existed. They were able to come up with a way to calculate the energy of the incident light. They were able to come up with a way to calculate the energy required to just remove the electron, which is called work function. And they were able to come up with a way to measure the leftover amount imparted to the electron in the form of kinetic energy, which is equal to 1/2 mv squared, which, by the way, I will remind you, is also equal to the stopping potential times the charge of the electron itself. Okay? So all of this work had already been done. What was missing for all of this is an explanation as to why. Because you remember from our first two videos here during the photoelectric effect that electromagnetic wave theory cannot explain this. So science was waiting for somebody to come up with a way to explain why this was all happening, and Einstein was the one that came up with the explanation. Let's take a look at some of the questions that were asked earlier and what Einstein's explanation for these was. All right, so we start off with, why does increasing intensity produce more photocurrent? Here's what Einstein said. He said, brighter light has more photons in it. In other words, more particles of light. Since each photon only removes one electron, more photons equals more photocurrent. So what he said was, only one photon is allowed to remove one electron from the metal. So if you shine brighter light on the metal, what that means is it has more photons, so it's going to eject more electrons, and therefore you get more photocurrent. That was his explanation. The thing that was probably really unclear to all the scientists listening to this presentation was, where did he come up with the idea that only one photon removes one electron? It's just what he came up with. It's what he thought. Next question. Why does increasing the intensity not produce more energy? And he gets to rely on previous work for this answer. And what he said here was because energy is only related to frequency of the photons, as the experiments by Planck and others had shown. Next question. Why is there a threshold frequency? There is a minimum energy that will just remove electrons from the metal called the work function. And this minimum energy requires a minimum frequency. You note here again, he's not really saying anything new. This had already been proven. But what he does is he emphasizes here the relationship between frequency and energy, that the frequency is what controls the energy. So if there's a minimum energy called the work function, that minimum energy would require a minimum frequency. And that minimum frequency is called, of course, the threshold frequency, and the symbol for that is FO. Why are electrons emitted immediately with low intensity? Presence of photocurrent is only related to presence of photons and not the energy of the photons. Okay? So all he's saying here is that photocurrent only depends on being hit by photons and has nothing to do with the energy that the photons have. Then, of course, in summary, the photoelectric equation, much similar to what we had up above, E equals phi plus Ke max. Substituting the equations for E and phi, we get HF equals HFO plus Ke max. Subtracting HFO from both sides, we get Ke max equals HF minus HFO. And then Ke max equals H times the quantity F minus FO, which simply distributed out Planck's constant. And we call that the photoelectric equation. That concludes our discussion on the photoelectric effect. Now on to solving problems.